Alrighty, welcome, or bienvenue, as they say in French. By request of my Year 11s, I'm going to do a bit of combinatorics. I'm going to do a couple of problems from the textbook just so you can see my thoughts. Maybe it'll be helpful in helping you see how you can formulate some strategies for doing questions yourself. But firstly, before we get started, we should talk about the fundamental things in combinatorics. That is, we should talk about permutation and selection. So, firstly, with permutation. Permutation, as I've written there already, is an ordering of objects. That is, we take some amount of objects from a group. We could take all of them. We could take some of them. And it involves two steps. It involves a choosing. That is, we need to choose how many we're going to take, right? And an ordering or an arranging, which is why you might see permutation stated as arrangement. That is, I'm going to choose some stuff and then I'm going to actually arrange it, right? This one is usually represented by NPR. Cool? Permutation, two steps, choose and arrange. Selection is slightly different, but fundamentally linked. That is, selection is just a choosing of objects. That is, it's basically permutation, but we don't care about how they're arranged. So we say it's only care about the choices, not how they're arranged, right? It's usually represented by something that we call NCR, that is, choose R things out of a group of N objects, okay? This is for when order doesn't matter, basically. Maybe we should write that. Order doesn't matter. Cool? One thing that I was talking with one of the other teachers about is we were talking about how there's a common misconception that can come up, particularly with choosing, because we live in a human world and when we choose stuff, we don't choose it in a vacuum. The important thing is that choosing isn't a time thing. That is, i.e., it doesn't care about the first, second, or etc. choice, just about what is chosen. So as an example, if I choose an apple first and then a banana second, that's a combination, right? Maybe I don't actually care about what order they're in. I just care that I chose an apple and I chose a banana. But that's the same thing as choosing the banana first and then the apple second. Or it's the same thing as choosing the banana second and then the apple first. That sounds a bit weird, but what I'm trying to get at is I'm trying to get at the fact that when we choose, because we live in a human world, we have to pick something first. But in a selection, we actually don't care about what is picked first. We just care that it's picked at all. Okay? So when you actually care about order, that is when you're actually going to pick them and then arrange them, that's a permutation. If you care about only what is chosen, it's just a selection, but it's not about when it's chosen. It's just about that it is chosen. Okay? All right, let's do a question. We're going to 10C, question 20, which is the last question in the textbook of that chapter. We've got a group of 6, and we're dividing it into, firstly, 2 equal groups, and then 2 unequal groups. So, 2 equal groups. Firstly, the way my mind works is I look at this and I go, we're dividing a group of 6. There's no specification about order, which means I'm immediately using combination or selection. Okay? Immediately a combination. And if I'm dividing into 2 equal groups, that means it's groups of 3, right? Which means if I want to choose, I'm going to choose 3 out of the 6. So I'm going to take 6C3, okay, which is equal to, let's just make sure I get this right because I don't want to get it wrong. It's equal to 20. Cool. Now, a common misconception people will make is they'll say, hey, I got to pick the first 3 and then I got to pick the second 3, right? And hopefully you can see the issue with that. That is, by the time you've picked the first 3, you've already picked the second 3. Let's have a look. So if I pick if I have 6 objects and I pick the first 3, so let's say I pick the top row, every time I pick a 3, I actually quote unquote pick the other 3, or I divide the group up already. There's no way that I can pick 3 and there be multiple options for the other 3. So really, the total number of combinations is just straight up 6C3, because every time I choose a group of 3, I'm automatically choosing the other group of 3, which means I've got 2 equal groups. Cool? So 6C3 equals 20. All right, 2 unequal groups. Groups have to be at least 1 person in each group, which basically just means we can't just have a group of 6 and then a group of 0, which is a fair thing to say. So the way my mind works with this, again, we're working with combination. Now, because we've got 2 unequal groups, there's going to be different cases. So let's split it up. Case 1 is going to be 1v5. Case 2 is going to be 2v4. Okay? Let's just do these first, and then I'll explain why we don't actually need to do the others. So, very similarly to the choosing groups of 3, every time I choose a group of 1, I'm choosing a group of 5, because I'm splitting it up, right? So the ways of making a group of 1v5 is really the ways of choosing 1 person, which is 6c1, which is equal to 6. Cool? The way that I make a group of 2 versus a group of 4 is I just have to choose the 2. So I go 6c2, which is equal to 15. Now, one might say, Mr. Long, there are other cases, aren't there? You've got case 3 and case 4, where you've got 4v2 and 5v1. Obviously, we don't do 3v3 because that's not an unequal group. And what I would say is your intuition is very correct. There are these cases, but if we actually draw them, we'll see that they're already being counted, and we don't want to overcount. Every time I make a group of 1v5, I'm basically doing this. 1v5, right? And every time I make a 2v4, I'm doing this. And that means that every time I pick a case of 1v5, I am picking a case of 5v1, because I could choose the first person, or I could choose the first 5. And these are exactly the same, right? Because it doesn't matter what order I pick them in, I just care about the fact that I split the group up. So, even though our intuition is correct that there are multiple cases, we don't count them all, because the order doesn't matter. So, we can write not needed and not needed, and we can just add the 6 and the 15, which is 21. Ugh. You could have also gotten 21 by adding all of case 1, 2, 3, and 4 together, but then recognizing that every case appears twice, so you divide by 2. Same thing. Awesome. All right, let's keep going. 10D question 5. Okay. A netball team of 7 is to be chosen from 6 men and 7 women. Find the probability that the selected team has more men than women. Now, fun fact, I actually play on a mixed netball team, and one of the requirements is that we have to have a maximum of 3 guys on the court at all times, which means that actually we do not do the maths, but we think a little bit about who can be on and who can be off and who has to take a sub. So maybe somewhat applicable. Anyway, let's actually do this question. So find the probability that the selected team has more men than women. Selection, meaning we're doing a combination. We don't care about the order of people. We just care about whether they're on the team or not, right? So we've got a couple of cases, right? But first, let's figure out the total, because it's always good to do the total first. So the total number of ways that I can pick a team is, well, it's just going to be the total number of people choose 7, because there's 7 people on the netball team. So the total number of people on the team is, well, to be chosen from is 13, and we're going to pick 7 of them, right? which is equal to 1716. Okay, so that's going to be the bottom of our fraction. Now we've got three cases to work with. There's three because we need more men than women, which means we go case 1, 4 men. Case 2, 5 men. Case 3, 6 men. And we can't do any more because there's only 6 guys, right? So now we just go case by case. So firstly, let's pick the 4 men. 6C4. There's 6 men and I pick 4 of them. Now, importantly, I'm going to pick a group of 7, which means I need to multiply, and I'm going to pick 3 more people. But I'm not picking out of, well, I've picked 4. I'm not picking out of the remaining 9 because I don't want any more men. So I'm actually going to go 7C3. Okay? Which is equal to 15 times 35, which is equal to 525. Cool? Then we're going to do the same thing for case 2. So pick 5 guys, 6C5. Then pick 1 girl, 7C2, or 2 girls, sorry, which is equal to 6 times 21, which equals 126. Cool, and then we're almost there. Last one, 6 men, which means we're just going to choose all the men. And there's actually 6C6 ways of doing that, or exactly one way of doing that. And we're going to grab the other girls. So 7C1, which is equal to 1 times 7, which is obviously equal to 7, which means we can write our total. And then we can just whack it over that total probability. So we can say, where am I going to write this? Let's do it over here. So our total probability is equal to 525 plus 126 plus 7 over 1716, which is 658 over 1716, which simplifies to, I think, 329 over 856. Okay, so just under half, which makes sense because there's less guys than girls. Cool. All right, onwards. 10D question 3. 3 letters chosen at random from the word heart and arranged in a row. Find the probability that H is first, H is chosen, and both vowels are chosen. Okay, so this question's kind of fun. So firstly, let's do H being first. Okay, if H is first, that means that I need to guarantee that H goes in the first spot, and then I need to grab the other 2. Cool. So firstly, we'll go, I like to do the box method. It's kind of up to you. We know that there's 3 spots. If H is first, there's only 1 option for the first box, and then there's 4 options for the second one and 3 options for the other one, which means it's a total of 12. Okay? The order matters here because I'm arranging them in a row. Okay? So this is a permutation. It's not a simple permutation formula because we've got a condition, which means we need to think about how the multiplications are working. So we know it's 12, and maybe we should have done this first. I'll write it in the bottom corner over here. We know that the total is equal to, we're arranging them, so it's 5p3, which is exactly equal to 60. Okay? So for this first question, the probability, I'm going to be lazy and just do this because I can't be bothered to write everything else, is 12 over 60, which is exactly equal to 0.2. Cool. All right. So the probability that H is chosen, this is where it's really helpful to remember that a permutation is choosing, then arranging. okay? Because we can't apply a simple permutation formula here. We can't just use an NPR. We need to remember that there's two steps. We need to choose the letters, and then we need to arrange them. And that's what it means to do a permutation. So firstly, we need to choose H. How many ways are there of choosing H? Well, there's only one way of choosing H, because it's 1C1. And then we're going to choose the others. This is where I said before that order of choices doesn't matter. I could choose H second or third. I just need to choose it, right? It's not about when I choose it, it's the fact that I do choose it. Then I need to choose the other two letters. Okay, 4C2 is the way of choosing the other two letters. And then I've chosen them. So to make it really clear, this is choosing. But I don't just need to choose them. What else do I need to do? I need to arrange them. And how many ways are there arranging three letters? There's exactly 3 factorial ways of arranging 3 letters. So this bit here, whoops, arranging. So this is then equal to, sorry, I should stay consistent with my colors. This is equal to 3 factorial times 6, which is 36. So our probability, again, I'll be a bit lazy with my notation, 36 over 60, which is 0.6. Cool. All right, then we're going to apply that very similar idea to C. We need to choose both vowels. There's only one way of choosing both vowels. That is 2C2, right? We choose both vowels, 2C2. Then we choose the last letter. We've taken both vowels, so we're going to take 3C1. Okay. And then, again, to make it clear, this is the choosing. And then we need to arrange them. Again, multiply by 3 factorial, because that's the number of ways to arrange 3 letters, which all equals 18. Therefore, the probability of both vowels being chosen is 18 over 60, which is equal to, I think, 0.3. Cool? Great. All right. Last one. Question 10D, or exercise 10D, question 10. A hand of 5 cards is dealt from a normal pack of 52. Find the probability that the hand will contain, and all of these different conditions, right? So I'm going to do decimal approximations here because that's what your book uses, but obviously we can write them as full fractions. The numbers just get really, really, really big. So firstly, let's do our total. We're picking a hand of 5, so our total is going to be 52C5, which is massive, so we're just going to leave it like that. Firstly, I want the probability that the hand will contain no aces. If there's no aces, it means how many cards are there left to draw in the deck? There's only 48, right? So I need to pick 5 cards from a choice of now 48 options. So my probability is going to be 48C5 over 52C5. That is picking a hand of 5 without any aces, which is approximately 0.659. Quite small. Well, actually, it's not quite small. It's more than half. All right, B, you could try to do case by case, but I wouldn't recommend it. We can take a sneaky shortcut. We need at least one ace, which is the complement of no aces, which means the probability, sorry, I should not be too lazy, is equal to, well, it's the complement, so we can pull a nice one, and we can do this. We should write approximately because we are using a rounded value. So it's approximately 0.341. Cool. All right. So C, the probability that I get the ace of spades. So if I want the probability that I get the ace of spades, it means I need to pick the ace of spades and then I need to pick the other 4. Again, order doesn't matter, right? So we're doing a combination. If I pick the ace of spades, how many ways are there to do that? I'm just going to do the whole thing as a probability because I think we'll be okay. The number of ways of picking the ace of spades is 1C1. Cool? And then I need to pick the other 4. So it's 51C4. And then I need to divide the whole thing by the total, 52C5, which is approximately 0.096. Now that is a lot smaller, right? Not crazily small, but considering the ace of spades is only one card, it's definitely significantly smaller than some other things. All right, the last one, the ace of spades, given that there is at least one ace. Given means conditional, which means we need to remember our conditional formula, that is PR of A given B equals PR of the intersection, A and B, over the probability of B. Okay? But we have a nice thing that's going on in this question, because if I have the ace of spades, I can say having the ace of spades means there is one ace. Okay? Which means that our probabilities, that is the probability of having the ace of spades and an ace, that is the intersection, is actually just equal to the probability of the ace of spades. Because having the ace of spades guarantees that you get an ace already, right? That is, we're not saying that you have to have more. In fact, the only way to get the ace of spades and an ace is to have the ace of spades, right? So now we can actually use our conditional probability formula, and we can say the probability of getting the ace of spades given an ace is equal to, we just said that the intersection is just the probability of getting the ace of spades. So the probability of getting the ace of spades over the probability of an ace. And we've worked this out before. Now, we should say a note. The question has told us that it's at least one ace. Okay? Which is important because it's not saying it's a singular ace. And we've worked out both of these probabilities. The probability of getting the ace of spades is up here. So we go 0.096 divided by the probability of getting an ace, which is over here, 0.341. So it's approximately equal to 0.282. Cool. If anyone has any more questions they want me to do, feel free to let me know. But otherwise, hopefully that's helpful.